there. A very warm welcome to yet another chapter of reading of biography of Albert Einstein with, I must change now the series name. It should be reading with only antenna radio. He is very naughty. He has become very naughty. He's in next room today, not even ready to come to this room. So yeah, but he's a good guy. Good. Very good. Everybody, I love you. Say I love you. Okay, don't say. So yeah, today the chapter which is waiting for us is very important chapter from the science perspective. To all the science junkies out there, this chapter holds a unique importance in today's time, and for every chemist out there and physicist out there, this chapter holds a very important place in their hearts too. I'm talking about quantum theory. Do you know what is quantum theory? Yeah? You know? Do you know? Okay. So, probably he has an idea. But yeah, let's get started. Another reading vlog, and trust me, once we are done with the chapters, all the chapters of this book, the level is only going to become bigger and better. So, quantum theory it is. In November 1922, when Einstein and Elsa were visiting Japan as part of an extended tour of the Far East, they received the news that Einstein had been awarded the 1921 Nobel Prize in Physics. So, Einstein received a Nobel Prize in 1921 in physics. Although Einstein was most famous for his theory of relativity, the prize was officially awarded for his work on quantum theory. That's very interesting. Throughout the first quarter of the century, Einstein made many important contributions to this field, the first of which was his 1905 paper on the photoelectric effect. From 1905 to 1923, he was one of the only scientists to take seriously the existence of light quanta or photons. However, he was strongly opposed to the new version of quantum mechanics developed by Werner Heisenberg and Erwin Schrödinger in 1925 to 26. And from 1926 onwards, Einstein led the opposition to quantum mechanics. He was thus both a major contributor and a major critic of quantum theory. Einstein's early contributions to quantum theory include his heuristic suggestion that light behaves as if it is composed of photons, and his exploration of the quantum structure of the mechanical energies of particles embedded in matter. In 1909, he introduced what was later called the wave particle duality, the idea that the wave theory of light had to be supplemented by an equally valid yet contradictory quantum theory of light as discrete particles. Many of Einstein's quantum ideas were incorporated in a new model of the atom developed by the Danish physicist Niels Bohr in the first decades of the century. Bohr explained that electrons occupy only certain well-defined orbits around a dense nucleus of protons and neutrons. He showed that by absorbing a discrete quantum of light, an electron can jump from one orbit to another. In 1916, Einstein found that he could explain Max Planck's black body spectrum in terms of the interaction of photons with the new Bohr's atoms. Although his arguments for light quanta were well founded, the physics community did not take them seriously until 1923. In this year, the American physicist Arthur Compton measured the transfer of momentum from photons to electrons as they collide and scatter, an observation that made sense only in terms of the particle nature of light. In spite of his contributions to the Bohr model of the atom, Einstein remained deeply troubled by the notion that atoms seem to emit photons at random when their electrons change orbits. He considered this element of chance to be a major weakness of the model, but he hoped that it would soon be resolved when the quantum theory was fully developed. However, By 1926, the problem of chance remained, and Einstein became increasingly alienated from the developments in quantum theory. He insisted that God does not play dice, and thus there is no room for fundamental randomness in physical theory. The year 1926 was a critical turning point in quantum theory because it witnessed the emergence of two new forms of quantum mechanics. The first, wave mechanics, was a mathematically accessible theory based on Louis de Broglie's idea that matter can behave as waves just as electromagnetic waves can behave as particles. This idea received its strongest support from Einstein, Planck, de Broglie, and the Austrian physicist Erwin Schrödinger. The opposing camp, led by the German physicists Bohr, Max Born, and Werner Heisenberg, as well as the American Paul Dirac, formulated the theory of matrix mechanics. Matrix mechanics was far more mathematically abstract and involved those elements of chance and uncertainty that Einstein found so philosophically troubling. In 1928, Heisenberg, Bohr, and Born developed the Copenhagen interpretation, which joined the matrix and wave mechanical formulations into one theory. The Copenhagen interpretation relies on Bohr's complementarity principle, the idea that nature encompasses fundamental dualities and observers must choose one side over another in making observations. This is better than quantum theory for sure. The communication that is happening between two rooms, between the two birds, radio and antenna, can't be separated, right? Look at him. He's making all sorts of beautiful sounds. Ollie! Come, radio! Radio! Come! Come to this room! Let's see. Okay, so where were we? The Copenhagen interpretation relies on Bohr's complementary principle, the idea that nature encompasses fundamental dualities and observers must choose one side over another in making observations. The interpretation is also based on Heisenberg's uncertainty relations, which state that certain basic properties of an object, such as position and momentum of a subatomic particle, cannot be measured simultaneously with total accuracy. Thus, the Copenhagen interpretation explained that while quantum mechanics provides rules for calculating probabilities, it cannot provide us with exact measurements. Following the formulation of this new interpretation, Born and Heisenberg proclaimed that the quantum revolution had come to an end. Quanta was a mere means of calculating probabilities, but did not account for phenomena as they actually occur. However, Einstein could not accept a probabilistic theory as the final word. As he saw it, the very goal of physics was at stake. He yearned to produce a complete, casual, deterministic description of nature. In an ongoing debate with Bohr that started at the Solvay conferences in 1927 and 1930 and lasted until the end of his life, Einstein raised a series of objections to quantum mechanics. He tried to develop thought experiments whereby Heisenberg's uncertainty principle might be violated, but each time Bohr found loopholes in Einstein's reasoning. In 1930, Einstein argued that quantum mechanics as a whole was inadequate as a final theory of the cosmos, whereas he was once regarded as too radical in his quantum theories. He now appeared to be too conservative in his defense of classical Newtonian ideas. In the 3 decades prior to his death, Einstein's distrust of quantum theory isolated him from the mainstream developments in physics. All of his greatest contributions to science had been made by 1926, and from this point on, he remained a staunch opponent of the theory he had done so much to build in his earlier years. Einstein focused his efforts instead on developing a unified field theory, a theory which would explain both gravity and electromagnetism in one principal mathematical account. He hoped to resolve the conflict between the smooth continuum of space time described by his general theory of relativity and the jittery submicroscopic particle world where quantum theory reigns. Although he never succeeded in this endeavor, in a sense, he was simply ahead of his time. Throughout the 1980s and 1990s, the primary goal of theoretical physicists has been the formulation of a grand theory of everything, or what they call TOE, theory of everything, that would account for every element of physical reality. And that's going to be very interesting when the TOE is out. Yeah, and this was me. I recorded without my mic being attached, so it's better that I give it to Antenna so that he can have a little fun. And I'm not going to re record, but I ensure the next audio is going to be better. So, see you next time. Say bye.